Alright, we're on the final part of this lecture today. Now, you don't have to look very hard to find people in your life, on the internet, wherever, that disagree with all this stuff. And one common argument they make is that none of this climate change stuff has anything to do with human activity and anthropogenic gases and so on. And often they argue, no, climate change is about changes in the sun. You can find these websites and so on where people say, no, this is actually about the sun and like sunspots and things like that. And that's one of those really tricky kind of arguments that has the problem of being kind of right. I mean, of course there's a connection between the output of the sun and global mean temperature. But it may not be as simple as you'd think, and of course there's a connection, but is it really meaning that anthropogenic climate change due to like greenhouse gas emissions and so on is wrong? Let's think this all through. The term of art here that we're going to be using is TSI, the total solar irradiance. That is actually the measure of the amount of radiation reaching the top of the Earth's atmosphere. We like that, and it's related to another concept you may have learned in another atmospheric or environmental science course called the solar constant. We're going to use TSI in this class. It's useful to talk about how much radiation actually gets to the top of the Earth's atmosphere, because once you get into the atmosphere, there's all kinds of complicated things that can happen, like absorption by ozone, reflection by clouds, reflection by the surface of the Earth, absorption by trace gases. Let's not get there yet. We got later modules, of course, to do that. We're just talking about what gets to the top of the Earth's atmosphere, what makes it through 95 million miles of cold dead space and gets here. And it is true that there are variability in the TSI. The sun does not produce the exact same amount of radiation all the time. That varies over a wide range of different scales, from billions of years to literally just days. We have to have a type of observatory that monitors how much radiation the sun is giving off, and we study it and so on. And what we know is that over the last 140 years, the sun changes all the time. It changes from hour to hour, from day to day. But the changes are relatively small. In fact, we can show, and we will be showing in just a few minutes, that solar variability doesn't do anything to explain the observed increase in temperature since the time when we started observing the TSI very directly using satellites. We started in the late 70s having satellites that weren't just looking down at Earth, but were looking toward the sun and very accurately measuring the amount of radiation coming from the sun, literally like minute by minute. And during that period, since the 1970s, I mean, that's like 40 years of record almost at this time, we've had global warming, and it turns out the amount of radiation receiving from the sun, which does vary, seems to have absolutely nothing to do with global mean temperatures. I'll show you that in just a few slides, but prior to the satellite era, when we could do this, TSI has to just sort of be estimated from sunspot numbers. We could do that all the way back to the early 1600s. Sunspots and the total amount of radiation the sun is giving off are very closely related. A sunspot is a part of the surface of the sun that's a bit cooler than the area around it, and therefore it gives off less radiation by Stefan Boltzmann's law. You might remember that from ATSEVS533. And so, yeah, if there's more sunspots, the sun generally is giving off less radiation, and if there's fewer sunspots, the sun's generally giving off more. So we can reconstruct the amount of radiation the sun is giving off all the way back, 400 years. And we can do this also with like radioisotopes that are trapped in ice and so on. I mean, that's a complicated story as to how that's done. And there are a lot of different things going on in the sun. There are these distinct periods of about 50 to 100 years where there's very little going on the sun. Where there's very few sunspots. Like, for example, where the sun is emitting relatively little radiation, like the Maunder minimum. We call those things the grand solar minimum, when there were few sunspots back in the... So let's be clear, it's called the grand solar minimum, but the sun's giving off a lot of radiation, okay? And then there's like another minimum, the Dalton minimum. I had never heard of that before I saw this particular diagram. And you can see how starting in the 1700s in particular, we really do monitor very closely the number of sunspots. And you can see that they have that cycle to them. They have about an 11-year cycle to them in general, for reasons that aren't entirely well understood. And when you take all that information into consideration, you find out that most estimates of the TSI changes between the modern minimum and the present day are only on the order of like 0.01%. In other words, we just haven't really resulted in that much more solar radiation at the present time than now that would explain the changes in temperature that have happened since industrialization. And that amount, I mean, that's roughly the same as the magnitude of the 11-year cycle. In other words, if the difference between the most radiation the sun gives off and the least it gives off in the 11-year cycle is about that same size, shouldn't we be seeing an 11-year cycle to the Earth's temperature? Well, in fact, if we take a look at just, say, the last 35 years or so, well, we can keep track of how many sunspots there were and so on. And we can use that to figure out like what the total solar radiation should be over that period. This is a direct measurement of solar radiation. And we can see, oh, there's this lovely, you know, cycle to it and so on. Global mean temperature doesn't look anything like that. Global mean temperature just trended up over that period. So global mean temperature is uncorrelated to like this 11-year cycle. So if the sun giving off 0.1% more energy in 1990 than it gave off in 1995 didn't make the planet warmer, why do we think it giving the same amount more radiation off since the 1600s is going to have changed the temperature? I mean, that's complicated, right? I mean, clearly global mean temperature doesn't look anything like this. On the other hand, global mean temperature is really well correlated to greenhouse gas concentration. We can take the last 400,000 years of global mean temperature that we get from things like oxygen isotope ratios, and we can get things like the carbon dioxide concentration that comes from trapped air bubbles in glaciers. Wow, this is a really close match. So global mean temperature seems to track pretty quickly carbon dioxide concentrations. But there seems to be the problem between this connection between solar output and global mean temperature. Now, let's not be stupid about this. Of course there's a connection between total solar irradiance and global mean temperature. That would just be, it'd be foolish to say there isn't a connection. Clearly the planet does warm as the sun gives off more radiation. It just takes a long time. Okay, 11-year cycles are too fast. That tiny flux of radiation from the sun of 0.1% greater, it's going to take forever to change the temperature of the oceans and so on with such a small radiative forcing. So we're not going to see it at like individual sunspot cycles and so on. So these folks who say, oh, the warming since 1975 is completely explained by... No, they're wrong. That's just a Facebook thing, okay? That is not what's actually happening here. Now, don't get me wrong, there is a connection both on the scales of thousands of years and even longer. I mean, on very long time scales, the sun has changed its output greatly. The x-axis on this diagram is in billions of years before present, and the y-axis on here is just the ratio of how bright the sun was at that time versus how bright it is now. So at the present time we have 1. And you can see if you go back 4 billion years, the sun was giving off 25–30% less radiation than it does now. 4 billion years ago, of course, there was at best single cell life forms and so on. But, the last 500 million years even, which is the Phanerozoic, the period since, creatures that leave behind skeletons and so on, we certainly have seen a few % increase in the total solar output even in that time period. But this explains, for example, why very weird things happened in Earth's paleoclimate history if you go far enough back. Perhaps the most dramatic such event was the so-called Snowball Earth. During Snowball Earth, the Earth became nearly frozen. It happened at least once, maybe twice. The records are in geological evidence is a little bit unclear about that. But it was a long time ago. It was 650 million years ago. This is long before creatures were crawling out of the ocean and all that kind of stuff. But the oceans froze nearly to the equator. The Earth became basically a white ball. The sun was just not emitting enough radiation. The Earth was too far away in its orbit. There weren't enough greenhouse gases in the Earth's atmosphere, and we ended up with a planet that nearly froze. But that can't happen in the present time. The greenhouse gas concentration in the Earth's atmosphere is higher, and the sun is 25, is several % brighter at this time. It's a perfectly normal thing, I don't think I mentioned that there, for the sun to do this where it increases in its luminosity. That is something that a main sequence star does. Over the course of its life cycle as a main sequence star, the sun will gradually increase the amount of radiation it's emitting. That is going to continue to happen for the next several billion years before bad things start happening, like the sun becomes a red giant that engulfs the Earth and so on. This is a normal part of the evolution of a main sequence a star. But keep in mind, it happens on a scale of billions of years. This does not explain why the climate today is warmer than it was 150 years ago. So paleoclimate research tells us that the last few decades of the 20th century were warmer than any time in the last 400 years, which is important information, but we can probably go farther back than that. It certainly is warmer than any time since the medieval warm period, which is like 1,000 years ago. But in fairness, the Earth has been both colder and warmer than it is today. We have had periods, we didn't get it all bogged down in some of these periods that were very warm, on the order of tens of millions of years ago and so on. But the Earth has certainly been warmer and been colder than it is today. But the current rate of warming is extremely rapid compared to what we see in the changes in the paleoclimate record. If you look back through past records, you never see such a spike as what we're seeing right now. That's not entirely true. In a later day, we're going to talk about the PETM. I can never remember what PETM stands for. That is a climate optimum that happened about 60 million years ago. That it happened very abruptly, similar to the current one. But in general, the natural variability does not seem to look like very much like what we're seeing during the anthropogenic era. The IPCC AR5 tells us that it is virtually certain that because of all these greenhouse gases that we're adding to the Earth's atmosphere, orbital forcing will not be able to create widespread glaciation for at least another 1,000 years. Now, I'm not entirely sure that I think that the Milankovitch cycles were expecting widespread glaciation on that timescale, but certainly on the order of a few thousand years to maybe 10,000 years, the Milankovitch cycle was clearly headed towards a new round of glaciation. We are nearing the end of this interglacial period and getting to the, on the order of a few more thousand years, we would be into the next glacial. And there's too much greenhouse gases for it to happen. Now, the IPCC says that it is virtually certain that that can't happen for the next 1,000 years. Other studies, remember the IPCC is just reviewing the literature. There are other studies with somewhat less certainty that say it's at least 50,000 years we can't get a glacial site. Oh, wait. We're basically missing the whole next glaciation at that point. Some studies say at least the next few thousand years. That's the next few million years, it would be difficult to get glaciation. Keep in mind, that is a big climate change driven long after we're gone. I don't know about millions of years, but certainly missing the next glaciation is an interesting event. It's hard to imagine that we could be affecting the weather and climate literally tens of thousands of years from now. So what all does the IPCC AR5 say about all this paleoclimate stuff? Well, they don't even bother attaching any kind of measure of certainty about it. They just say point blank, it is a fact that present day 2011 has happened to be when they wrote that part. Concentrations of the atmospheric greenhouse gases, carbon dioxide, methane, and nitrous oxide exceed the range of concentrations recorded in ice cores any time in the last 800,000 years. Okay, we currently have more of these radiatively important gases, which we'll learn all about in later modules. We have more of them now than any time in the last 800,000 years, for sure. Okay, it's a fact. With very high confidence, we can say that the current rates of carbon dioxide, methane, and nitrous increase in the concentrations is unprecedented with respect to the highest resolution ice cores of the last 22,000 years. In other words, the last 22,000 years, where we have the best information, nothing about any of that we ever have seen in there about the rate of increase of carbon dioxide, the rate of increase of nitrous, and the rate of increase of methane ever looks like this. Oh, ouch, that doesn't sound good. Okay, so we've definitely done something strange. There is a high confidence that changes in atmospheric carbon dioxide concentration are playing an important role in these glacial-interglacial changes. There are the periods of these ice ages and the periods in between them are primarily driven by Milankovitch cycles, but the IPCC says that there's also high confidence that there's feedbacks involving greenhouse gases. As the planet gets more covered with ice, carbon dioxide concentrations in the atmosphere will increase and will start warming, and that's part of how we get rid of the ice age at the end of it. There is very, very high, though this one's scary, there is very high confidence that the maximum global sea level during the last interglacial period, which happened like more than 100,000 years ago, was at least 5 meters higher than present, and probably not more than 10 meters above present. It's probably about 6 meters higher than above present in that period. So in the last interglacial period, the last time the glaciers were all gone, sea level was probably about 6 meters above normal, above present. Let's see here. So in other words, the last time we were between ice ages, sea levels were a whole lot higher than they are now. I mean, we're worried about sea level increases, and we've only increased the height of the sea level by like a few meters. I'm sorry, a few inches. 10 inches, I think, is the number we had. The last time it was an interglacial, they was 6 meters. And here's the deal. Temperature reconstruction showed that with medium confidence, the global mean annual sea surface temperatures were never more than 2 degrees Celsius higher than the pre-industrial level. That's not far from where we are now. Okay, we're nearly 2 degrees above pre-industrial. In other words, back in the last interglacial, when sea levels were so ridiculously high, they were about the temperature we are now. Okay, we're not, maybe a little bit, maybe a fraction of a degree cooler than that, but we're headed towards 2 degrees and more. Heavens, climate treaties are like ambitiously hoping to keep climate change limited to 2 degrees Celsius. 6 meters of sea level change would happen if we only get 2 degrees of global warming? Oh my. Oh my, that has major consequences for like urban environments that are along coastlines and so on. That's bad. That's long-term bad. There's high confidence that an annual mean surface warming since the 20th century reversed the long-term cooling trends over the last 5,000 years in the Northern Hemisphere in particular. In other words, as we came out of the Holocene climatic optimum, it looked like there was a long-term trend as we were heading into something, some kind of stadial period. That's gone. That's not going to happen now. We are the addition of greenhouse gases has made sure that long-term that trend on the order of like 5,000 years, that has stopped. Huh. Man, this paleoclimate stuff is cool. Man, I love what they can find out about the world using all these cool proxies and so on. I love talking to former students who work in that discipline now and people I went to grad school with who do that stuff now. It's unfortunate, of course, that all the news is bad. But you know what? All we can do is have information and work with the information we have. And if the news is bad, the news is bad. Alright, this brings us to the end of Module 1. I'm going to ask you a couple quick questions, but we are now done with Module 1. There's going to be a review, but then you're going to be taking the exam in the coming days, alright? Let's just wrap up with a couple more questions. Again, one that actually came from a past quiz or past exam or something like that. The Little Ice Age would be an example of blank. A stadial, an interstadial, anthropogenic climate change, or an interglacial. You gotta know what this word stadial and glacial and interglacial and all that kind of stuff means. Which of those is the correct description of the Little Ice Age? Make a choice from those 4 options to get a little feedback before you go on to question 13.